There we go. Okay, nice to see you guys. Thank you for coming. Awesome. Okay. I went down to NVIDIA yesterday. NVIDIA has a new chief scientist slash vice president of NVIDIA research. And it's my PhD advisor, which works out pretty well for getting access to that sort of thing. So that was really enjoyable. So I also sat down with the main guy with CUDA. So I had some interesting questions about that. So anyway, it was a good visit. What we're going to be talking about for the next 5 lectures is pieces of the graphics pipeline. So basically, I'm talking on Tuesdays, and we have guest speakers on Thursdays. So today's a Thursday. I'm talking now, and then every Tuesday from now on, I'll do another piece. So hopefully we'll get through most of geometry today. So I want to make sure after you're done that you really understand what the steps of the pipeline are, and also how people implement pieces of these steps. So what actually goes in hardware to build these things. The other thing I want you to think about is that as time is going on, some of these steps are becoming more programmable. And so the interesting thing is what, at this point in the technology curve, should be programmable and what should be fixed function. And that changes as the technology curve moves. So a lot of the pieces I'm showing here remain fixed function in current GPUs, but they might or might not be moving to general purpose in the future. And so to think about what the differences of efficiency are, because it's very efficient to be able to build something in hardware. But is that where you want to put your design effort? And is that where you want to spend your transistors? So this is really the question that GPU architects are thinking about right now. They've got this enormous list of features they need to support. What do you do programmable, and what do you do in fixed function hardware? Okay, so we talked about big trends when we talked about the VLSI lecture that we did on Tuesday. So one of the trends was we have more stuff to play with, and that's obviously good. That's why I'm very excited to be a computer engineer. If you work in Detroit and you're building cars and you make something go 0.5% better, you're a hero. Okay, well, we get like twice as much stuff to play with every 18 months. And so our performance curves are going up 40% a year. And so that's much more exciting than 0.5% a year. That's cool. The second thing is, so what can we do with this? Okay, so this is what I want you to think about as we talk about these different stages. Hey, we got more stuff to play with. What are we going to do with it? Well, it's going to run faster, but we're also going to think about new features. What can we put in this part of the pipeline so that we can do newer, cooler, better kind of stuff? Okay. The next thing is ratio between off-chip communication and computation. Okay, so getting cheaper, communication isn't really getting cheaper, and so that's an enormous mismatch in terms of technology rates that change the way we're thinking about graphics architecture. So one thing I'll be talking a good bit about today is vertex input bandwidth. So we send vertices from the CPU to the GPU. Okay, those vertices take up a lot of bandwidth. And that's sort of the slow part, right? And it's getting slower as time goes on. What can we do to reduce the cost of that? Okay, so that's something we want to think about. How do we reduce the cost of input bandwidth? Is there any place where we're computing rather than communicate? Okay, if we could, we might have the choice to send something again or to recompute it. Okay, we'd like to recompute it more and more often. How are we using caching and replication and prediction in these pipelines? Okay. And finally, on-chip communication is getting more costly. So what can we do to take care of that? And so power is also important there. I don't know that I'm really touching about this too much in the geometry pipeline, but in general, I want you to think about these 3 things as we talk about pieces of the pipeline. Okay. So what are we talking about today? We're sort of talking about the back end of command stuff, sort of how we sequence things up. But mostly we're talking about the geometry part of the pipeline. All right. What comes in is a bunch of vertices and a bunch of connectivity information. Okay. What goes out is triangles in screen space, and they're going to be ready to rasterize. So how do we do this the most efficiently? So in particular, what I'm going to be concentrating on here is having faster processing, what the new features are that we put in, and how we deal with vertex bandwidth. So these are sort of the things that I'm concentrating on today. Okay. So the first thing we're going to talk about is homogeneous coordinates. All right? And so we talked a little bit about this earlier in the pipeline. Okay? And the issue is that we need to specify a point in 3 space. Okay? Somewhere out in 3-dimensional space, like the kind we live in. And it's natural for us to think that, hey, it's a good idea to do 3 coordinates to represent 3 space, x, y, and z. It turns out in graphics what we actually do is x, y, z, and w. And I hope that I'm going to motivate that in the next few slides. So the question is, why do we put in this extra coordinate? So first, what is this extra coordinate? All right? So these two things are exactly the same. All right? The extra coordinate is actually redundant. So you can always divide out the extra coordinate. Okay? It's just a scaling term, and you should think about it like a scaling term. Okay? And so anytime you have something with a non-1 w, you can divide through by w and come up with a 1 here, and it's going to be the same point in space. Okay? That makes sense. Everybody cool with that? All right. What happens if I put in a 0 for w? Okay. So then you divide through and you get infinity. What does that mean? Okay. What does it mean if I specify a 4 vector and the w term is 0? There's some infinities in there, but what does it mean?
Depending on what the x, y, z terms like negativity or whatnot, it's from the world space. It's like as far out as you can get it.
Okay.
At a certain depth.
It is, and let me sum that up in one word, a direction. Okay? So if my point is 1, 1, 1, 0, okay? Well, that's the same thing as infinity, 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 1, sort of, because you're dividing through by 0, and dividing by 0 is always a crazy thing. But what this means is a direction in the 1, 1, 1 direction. Okay, so if I'm here, and this is x, y, z, it's out there in that direction. All right? If I change this to a 2, okay, then we have sort of 2 times infinity. Okay, so that's 2 in this direction, 1, 1. So it's going to be sort of out this way instead. Okay? So this is a natural way to think about it. I mean, you want to think about it as a direction because it really is out at infinity and it's telling you a direction. But it turns out all the math, it works out very nicely too. Okay? The math actually works out such that this is, in fact, a direction. So homogeneous math is really very cool. So first thing we're doing is we're saying, all right, we're introducing this new weird w term. At least first I've told you what this w thing is. Okay, so you're going to say, well, okay, John, that's cool. We have this w term. We know how to work with it, but why do we deal with this? This seems like a big pain in the butt. So why do we do this? It allows more general transformations. And I'll get to that on the next thing. So take this on faith right now. So the next slide I'll talk about this. You can do more general transformations, and we'll talk about what kind of transformations with a 4 by 4 vector times a homogeneous coordinate than you can with a 3 by 3 vector times a 3 vector. So take that on faith. The other thing is that this divide historically has been expensive. Okay? You have to do a divide on every vertex. Floating point divide isn't cheap. Floating point divide especially isn't cheap if you look at hardware in 1982, like when Jim Clark made up his the first geometry processors. Okay, so if we can push off this divide until we actually have to do it, that's better. Because if you do a whole bunch of processing at the front and you decide you don't need it anymore, and then you can throw it away and you haven't had to do the divide yet, then you saved yourself a divide. So any sort of vertex processing, you could do the divide up front if you wanted to. It's just you might be throwing out the vertex later on, and then you spent that divide for nothing. So we're being lazy. We don't want to do any computation that we don't have to. Okay, so on matrices here. So typically in floating point pipeline, this is done with single precision floating point. We deal with 4 by 4 matrices to express transformations, and they're multiplied by 4 vectors that are expressing our points. All right? You remember we have more than one matrix. We have a model view matrix in GL, and we have a projection matrix in GL. So if we have the expression that we're going to take some sort of point and we're going to multiply it by the model view matrix, and then we're going to multiply it by the projection matrix, okay? Well, we can compose those two into one giant matrix, super M times the point. Okay? Who does that composition right there? Okay, well, that depends. You can either have the application do it or you can have the implementation do it. So the graphics hardware can be in charge, or the OpenGL stack on the CPU can be in charge. Now, talk about transformations for a little bit. All right? what a 3 by 3 matrix can express is what we call an affine transform. Okay? So an affine transform, by definition, will preserve parallelism of lines. All right? So I have two lines right here. I can do transforms that are affine if I move. Right? Translate. Okay, my lines don't change. I can rotate, and the lines don't change. I can scale. Okay, so you can take and stretch it. And you can stretch it in different ways. Like I can stretch this way, but the lines themselves are not going to change. Those are affine transforms. Okay, those are useful transforms. Okay, so we want to be able to express those, and a 4 by 4 matrix will allow us to do that. However, perspective projection is not an affine projection, and so the picture I always draw for that is you have this nice horizon here with the sun and happy clouds and train tracks. Okay, and I'm standing right in the middle of the train tracks, and hopefully I'm not going to get run over by the train. All right? Well, in world space, in real life, these train tracks are obviously parallel. Right? Train tracks are parallel, or else it would not be a very successful train. But when I do a projection, this transformation here, okay, these train tracks are no longer parallel. So the transformation that I did, which happens to be this perspective transformation where things that are far away are smaller than things that are close, is not an affine transformation. I can't express something like this with 3 by 3 matrix transformations. Instead, I need a more general transformation. And that's why we use 4 by 4 transformations. They let us do more, cooler, better kinds of transformations than we could otherwise do. Okay. So here's an example of a couple of these. So this is what the frustum looks like, and this is what the perspective looks like. And they're kind of similar, which is good. The frustum is sort of a lower level thing. Basically what you specify is the position of left plane, right plane, top plane, bottom plane, near plane in the z direction, and far plane in the z direction. Okay? That's not necessarily the way that a programmer would necessarily want to specify the projection. So instead, sometimes it's useful to use perspective, where you're instead using far and near plane. You use the F is it focal length? Is that right?
Field of view.
Field of view, thank you. Field of view. Okay, field of view, so what's the fraction that you can see? Okay, are you looking like this or big wide? And aspect ratio, so sort of what's the size of the TV that you're looking at? Okay, is it square? Is it rectangular? So on. Thank you, Wes. So this is maybe a little bit easier. You don't have to deal with specifying where the top and bottom and left and right planes are, which is why this is GLU and a little bit higher level than that GL. Okay, but we note that these are planes that are, note that they're using all 4 rows and columns in the transformation, which is good. Okay, so we're going to do a bunch of transformations. Right? Let me just briefly talk about what these transformations are and what we're doing between them. So what I'm going to do is walk from the top to the bottom. So what we want to take is something out there in its own object coordinates in world space, or some sort of its own coordinate system, and eventually get it down into 2D window system coordinates. So all the objects might be in their own object space, but by the time they get here, they're going to be all in one common object, one common screen space. Okay. So the first transformation we're going to do is from object coordinates. Right? So we're designing this giant cool game, and the way we decide to do it is everybody ends up designing a different monster. Okay? Each one of you guys gets to design a different guy for this game. Okay? Each one of you is going to want to model in your own space. So it's very convenient to model in object space. None of you have to know about anybody else's object space. And it might come back and, one of you's used an origin here at the top of your monster's head, and one of you's used, the origin at the bottom of the feet, and one of them has one like at the base of the spine. You can pick any coordinate system that you want to do this. Some of you have height in the z direction, some of you have height in the x direction. Doesn't matter. Okay? You can get a model in any object space you want. And then the model view matrix is going to turn it into some sort of global-ish thing where it's all going to be in the same space. That's what the model view matrix is going to express. It's the relationship between object space and a common I space. Okay. So next we go to I space. And one of the questions is, why do we go to I space in the first place? Okay. Well, I space is the only real world space in this whole pipeline. Okay? It's the only place where we're in natural 3D space before we do any of the perspective or anything. And so it makes sense to calculate lighting in this space. Okay? You're in a common 3D world space. You have a sun out there. Okay? It has a real direction. You can calculate what the direction is. It's obviously going to influence your lighting and so on. Okay? And everybody has the same coordinate system there. So historically, iSpace has been used for lighting calculations. We took every object, we brought it into iSpace, and we lit the object in iSpace. Okay. Now, how many objects are in a regular scene, roughly? Or how many vertices are we going to have? Or how many triangles in a scene? Order of magnitude. 100,000. Great. Perfect number. How many lights are in a scene? 5. Okay. Are there more lights or are there more objects in a scene? Probably objects. So does it make sense to do all the objects to here, 100,000 objects to there, or does it make sense to take the lights and back project them into object space? Now, you're going to have to back project them into every object space because different objects have different space. Evidently, I am now told that modern renderers back project the lights into object space, calculate all the lighting in object space, and then just totally skip the iSpace. Okay? What that means is we're going to end up doing this in the application. Somebody's going to end up doing this, that there is no intermediate step anymore, at least in a modern renderer, between model view and projection. We don't go into iSpace. Instead, we just sort of lump these two things together and go straight from object space to clip space. Okay. GL also defines user-specified clipping planes, which means that you can specify a whole, basically there's a tool, all right, there's this visible human kind of guy. And it's like you do a volume renderer through them, and there's a tool you can use called a paddle, and you can specify where the cutting plane is. You can say, okay, draw everything on this side of the plane, but not this side, and so then you can sort of walk through the volume and see the intersection of your plane. So that's usually a user-specified clipping plane. It says these things are visible, these things aren't visible. So if you specify these in GL, then that clipping plane is applied in iSpace. You specify it in iSpace. Okay. So, up to this point, we're still in 4 space. Okay, we still have homogeneous coordinates. Okay, haven't done any perspective divide yet, so that's kind of cool. The next place we go is clip space, and we'll talk about this in a little bit more detail. Okay, so find an eraser. Okay, so eventually, we're going to have some sort of space that looks like this. It's going to be a nice box. Okay? And this is going to be the front plane. That's going to be the back plane. We're going to have left, right, up, down planes. Okay? We would like to clip against this space. Okay? We want to keep all the things in this space in our viewing frustum. We want to throw away all the things that aren't in our viewing frustum. So the projection matrix basically puts everything in this box that's got it's got 6 sides to it, and we want to throw out everything outside the box. Okay? These things we want to throw out, these things we want to keep, these things we want to clip. So we're going to have to make that decision. Okay, so the nice part about clip space is that you can clip in 4-dimensional coordinates. You can clip with your homogeneous coordinates. Right? So let's say I'm designing this space, and I say, okay, that's 0, 0, 0. Okay, and this is 1, 0, 0, and this is 0, 1, 0, and so on. Okay, so basically, what kind of test do I need to do on a triangle to, if it's in 3 space, to be able to decide if it's being clipped or not? Okay, so if I just want to look at this point, what am I going to decide to figure out if it's in this box or not?
If you just multiply W by the...
Just in 3 space first. Right, so this point is x, y, z. Okay? What's the test that I need to do to x, y, and z to say this point is in that box or not in that box?
Greater than x. Oh, x is greater than x min, less than x max.
0 and 1.
Yeah, y is greater than y min, less than y max. Greater than y, less than.
Okay, in this, exactly right. In this space, basically what I'm saying is x between 0 and 1. Y between 0 and 1 is z between 0 and 1. Okay, so that's pretty fair. So let's say my point is x, y, z W. Okay, now what am I testing against?
You can just multiply, your edge points by W.
Right.
See if that still matches.
Okay, so this point, rather than being 1, 0, 0, is now W, 0, 0. Okay, this point is 0, W, 0. Okay, so now I test if X is between 0 and W. Okay, but notice I can do that test without ever having to divide out anything, right? I've never had to do a divide. I didn't have to do this perspective divide. I didn't have to convert this point to X, Y, Z, 1. Okay, so if I clip things, if things fall out in the clip phase and I throw them out, I've never had to do the divide on them. And that's good. So this is another motivation why having homogeneous coordinates is good, right? I've never had to do the perspective divide. So I need homogeneous coordinates, but I want to delay computing them as long as possible. And I've delayed computing them until the clip phase because I can clip even without doing the perspective divide. That's a big plus. Yes?
Is there a reason that you, because all the objects outside of your clipping blocks, those get lighting calculated for them as well as the object, the model view matrix has to be applied to them and stuff. Mm-hmm. So why don't you do, why isn't clipping done first?
Okay, so there's going to be a lot of questions like this that come up. Why do we do things in this order? Okay, this is a great question. Why don't we try to move clipping up above object and above the lighting calculations that were done here? Okay, so that's a good question. So you're kind of trading off between there's work to go from here to here, and there's work to be done in here. Okay, so I guess one thing, and it would make more sense today to be able to do that. You comment?
It might be that like an object, even though it's outside of the clip space, might affect the size of another object inside the clip space. Okay.
And while that would be cool, it would be a very bad thing in the modern graphics pipeline if we did that. Okay, so let me be very clear that every vertex is calculated without knowledge of any other vertex. Right? Every vertex is parallel. Okay? If you have one vertex in front of another vertex and it casts a shadow, don't know about that. Right? We're ignoring that sort of thing. That's why shadows are hard. Okay? There is no way that the calculation of one vertex is going to affect a different one, or else things would have dependencies on them. And the whole pipeline is designed so there's no dependencies between different objects that are coming through it, as much as possible. Okay, so that's a really important thing to point out. Okay, so then the question would be, could you design this pipeline such that you sort of ran through the two matrices as soon as you could, okay? Then you had to, then you clipped there. Then you took the things that were left, and you'd have to go back into I-coordinates to calculate them. Okay? And then you calculated the shading there. Okay? So, historically, this is probably, this is a good question. Nobody's asked me this question before. Historically, probably the cost of keeping around that extra state, keeping around the position and so on, was greater than that of actually doing the lighting. Today, probably the lighting is a more expensive thing. You would probably want to defer shading as much as you can today because lighting is more expensive to do. Yes?
It seems like moving, it doesn't matter how many stages you move up or down, you're just multiplying by one matrix. Because you can say you want to go from all the way to object, you can multiply the projection by the model view. So it's not like you're doing projection matrix and model
That's
view.
true.
You're just doing one step anyway.
Yes.
So it's always one step.
Okay. And one thing to keep in mind is that this is the way that GL specifies it. You can compute it in any way you want. It would not surprise me if the modern implementation was going to defer shading because it was going to be cheaper. Okay, a modern, at least some modern NVIDIA hardware, and I think they've gone back on this now, doesn't actually do the clipping until way later in the pipeline. They actually don't do it until rasterization. So they have a clipping rasterization algorithm that does the clipping at the same time. Okay, there's a lot of trade-offs here. So from a software point of view, it needs to at least behave like this, but it doesn't have to look like that.
So one reason that it may become impractical to move clip earlier in the pipeline is that the clip operation can potentially change objects that go through it. So the triangle that is partially in and partially out, that clip operation is going to compute the position of a couple of new vertices. And what color should they be?
So when we clip, right, if this guy is red and this guy is green and this guy is blue, we're going to have to figure out what it is here and here before we can do anything with this triangle. So that does add a little bit of computation or complication. You can clip and come up with multiple triangles. And one of the nice parts about the way things are organized right here is you're always only going to compute one triangle. And if you clip against this plane, you can come up with many triangles, and that would be more work to do, because then you'd have to do all these intermediate points, because you can come up with more than one triangle out of it. Yeah, so I haven't heard anything that they're doing this. I think the question is a very good one, and it's something to keep in mind. You know, technology is changing, first of all, but also the characteristics of the graphics pipeline are changing, and it's getting more and more expensive to shade. So the things that are getting more and more expensive compared to the other ones, we should try to move them down. We should try to do less of that because that's getting more expensive. So I like the question. Okay. Cool. Now, so clipping is also the place where we have to assemble the triangles. Okay, because clipping, everything above this has been things you perform on vertices. Okay, what color is this vertex? That's what you're computing. At some point, you have to go from a bunch of vertices to a bunch of triangles. And the place where you want to do that is clipping, because you don't clip individual vertices, you clip triangles. So, you know, it doesn't do any good for me to know that red is in and green is out and blue is out. I actually have to know where they are and know that's a triangle and produce new vertices as a result. And we'll talk about clipping a little bit later on, but this is the point where triangle assembly happens. Okay. Next place we go is what are historically called normalized device coordinates. Keep in mind that today pretty much we go straight from clip to window. But this is a nice abstraction to be able to think that once we do this perspective divide, and now we have XYZ, not XYZW, we can do culling here. Okay? And we'll talk about how culling works too, but let me give you the heads up on culling. Culling is saying we're rendering my head, and it's a big circle, big sphere. Okay? So then we're going to render everything on my face, and we're going to render everything on the back of my head. None of you guys can see the back of my head because the face is in the way. Essentially what we're going to try to do is we're going to say everything that faces toward the camera, okay, is something we can see, and everything that faces away from the camera is something that we can't see, so why bother drawing it? Okay, so how do we figure that out? We'll find that out later in the lecture. Okay, that's culling. But you can compute it very nicely in this space after the perspective division, if you choose to, and we'll see how that's done. Okay, final one's very simple. We go from 0, 1 or -1, 1 into the screen. So it's a very simple transformation to be able to do. It's just a 2x2 matrix multiply. And then finally we're in window coordinates. Okay, that's a lot of stuff going on there. Right? There's a lot of coordinate systems, but these are, and they're not, we don't have to do all of these, but what I hope you're getting out of this is there's useful work to be done at any of these, and all of this work needs to be done. Yeah?
So I like the question about, why not move clip earlier? And so in that spirit, why not move cull between eye and clip?
Okay.
Because
we get rid of stuff.
Yeah, because when stuff is in the eye coordinate system, then all you have to do is look at the z component of the normal vector, and you can make a decision that way. Okay.
So one of the questions we have is, are we clipping based on the normal? Okay. So that's what Wes is suggesting. He's suggesting.
Culling.
Sorry. Are we culling based on the normal? So what we want to find is the triangles that are facing the screen and not the triangles that are facing away from the screen. And I hope this is clear. If they're facing the screen, it means that that they should be visible, right? If you can see all the triangles that are facing you, all the triangles that you can't see are not facing you. So it makes sense to throw out these triangles. Okay? So one of the questions is, how do we decide what to cull or not? One way we can decide if we're culling or not is we can look at the normal vector and say, is the normal vector facing the screen or not facing the screen? And that is not the model in GL. The model in GL is that we do not have a per facet normal. Okay, we don't have a normal per triangle. Instead, we have a normal per vertex. Okay, so what happens if you have a triangle where the two normals are facing the screen and one is not? Do you throw that out?
That's a lousy triangle. Throw it away.
Okay, Wes doesn't like that triangle. But in here, you might be doing some crazy bump mapping stuff and messing with the normals. Okay. The second thing is, so that's one answer, that you can't use the normal vector, at least in GL with the GL model, to determine whether something is facing the screen or not. You actually have to look at the triangle and figure out which direction is it facing. And we're going to see how we do that. The second thing is that this perspective division is going to end up doing some things to triangles that are not obvious. It will, it's much easier to tell if it's facing the screen after you do the perspective than before you do the perspective. Okay, so the math is very simple here to do culling. The math is more complicated up here. I don't doubt that it's possible. What I am presenting here is the OpenGL view of the world. It doesn't mean that an implementation has to do it, but it's very natural to think about doing it here. I'm very happy you're thinking about ways to move it, and I know that different implementations will move it. So it makes a lot of sense to take things that throw out work and move them as early as possible. It is worth doing extra work to do that, probably, because this part is getting so expensive with the shaders. Okay, so what you're saying is very sensible. I'm just presenting the OpenGL view of the world. Okay, and regardless if it's efficient or not, this is a very natural place to put all this math. Okay, it is the natural place to do the cull here, because the math is the simplest here. Okay, so what things do we have to worry about in the geometry pipeline? Okay, we have to worry about vertex operations, okay, things that happen to every vertex on its own without knowing that it's part of a triangle or anything. So some operations in the geometry pipeline are done on vertices only. Okay, we do the transformations on vertices. We don't care if they're part of triangles. We don't care about that at all. If we deal with the normal vector, okay, we normalize the length of the normal, and that's useful in lighting. We'll see how lighting works. Okay, we compute the lighting, and we do texture coordinates. Okay, so this is sort of all the things. These are things that are done only on vertices. Some things we do on triangles. Okay, so we have to assemble the vertices into triangles, and clipping is only done on triangles. And if we do culling, we're throwing away all the triangles that are facing away from us. These are operations that are done on triangles. Okay? These are things that are done on vertices. These are things that are done on triangles. So if you're building this in hardware, you have to deal with two different sort of granularities of things. You have to do things on individual vertices, which are parallel. But then there's some dependencies that go on that assemble them into triangles. And then you do things on triangles, which are also parallel. So that makes it a little bit harder, this triangle assembly phase. Okay? It's tricky because you have to put the triangles, put the vertices into triangles. Okay. So going back a second here. Okay, what are we actually transforming here? Okay, what is the object that we're transforming? It's a valid question. We're transforming positions, right? Okay, when we go through all this, we're taking a point, we're taking its position, and we're transforming it into object space, eye space, clip space, and so on. Okay? Now, we also have to transform normals. Okay? So if I design this guy in this coordinate system here, and I transform into eye space, I also have to take the normal vectors that I have and transform them into eye space also. Okay. So remember we talked about how XYZW is a point if W is not 0, but XYZ0 is a direction. Okay? It is good for you to think about a normal vector being a direction. Okay? It is sound mathematically to you to think about that. And so the math ends up working very, very nicely, such that when we transform a point with a particular matrix M, we should actually transform the vector with M inverse. Okay? I can't even explain to you why that's the case here, at least not well. I'd have to do a lot of math to figure that out. But you'll just have to trust me that that's the case. It makes a little more sense to transform it with M inverse, where M is a 4x4 matrix. But it turns out that the OpenGL, well, the math works out such that you can do it with a 3x3 matrix and pretty much get the same answer. And the GL spec tells you that you can use either one of these if you choose to. So that means that you have to get M inverse. Every time you change M, you better also change M inverse. And so there's different ways you can think about the hardware doing that. You could say, okay, well, every time I change M, I'm going to recalculate M inverse, or like maintain those separately all the time. So whenever I change M, I'll also change M inverse. You can recompute it every time you change the matrix. So you change M, and then you'll change M inverse. Or you can make M, you can make the application specify it and say, oh, I'm changing M. The application also says it needs to change M inverse. Okay. So why do we transform them? The particular place usually where we have to transform them is object space into I space, and we do lighting in I space. So we have to transform them to make that work properly. So there's issues there because your model view matrix might not be rigid. So rigid in the sense that your model view matrix might not maintain parallel lines. It might not do an affine transformation. And that makes it tough mathematically. So that's the tricky part. But yes, this is what's commonly done. Okay, the other thing you deal with is that you specify a bunch of normals in object space, then you have to transform them into I space. So that can change the length of the normals. Okay, and the length of the normals is important. And so usually, to do good lighting calculations, the lighting equations require that all the normals be unit length. So you can set something in GL, part of the state that says GL normalize. And then when you transform normals, it will also automatically normalize them. So it does a little bit of extra math to make sure that all your normals, once they reach I space, become normalized. So you can set that, or you can do it yourself if you want to. Okay. So one of the way that you normalize, so we have vectors x, y, z. Okay, and we want to normalize it. What we do is we take x over square root of x squared plus y squared plus z squared, right? This is how we figured out. So we do x over this, y over this, z over this. Then that vector is of normal length. Okay, the length of that vector is 1. So this particular operation is something that graphics hardware should be able to do very well. Particularly what we want, we don't care about reciprocal. We care about reciprocal square root. Okay? So we would rather have a reciprocal square root than just about any other kind of weird divide or square root or any other kind of thing in our graphics hardware. If you remember the original vertex shader standard that we looked at, there were 17 instructions in vertex shader 1.0. Okay? One of those was a reciprocal, and one of those was a reciprocal square root. This was so important that it was one of the 17 instructions. You have to be able to do this fast. Okay, lighting. So I have just one slide on lighting. This is showing what the OpenGL lighting model is. Right? So we have a light. We have a point that has a particular vector. And we want to figure out what color we're going to assign to that point. All right? So the OpenGL guys could have done all sorts of things here. What they decided to do was something that basically looks pretty good and is not physically relevant at all. Okay? There's very little that's physically accurate about this, but you can do some interesting things with it. So we have a bunch of terms here, and let me sort of tell you what the terms are. All right? The color, when you go through the lighting equations, are the emissive component, this E. So that's saying, which is totally not physically correct, that even if you put this object in the dark, it's going to have this particular color. Okay? This guy's going to be flat gray or bright red or whatever. Okay? Not physically realistic at all unless you're like fluorescent. So most things do not actually have an emissive color. Okay? But it's in the standard. Okay? Ambient. Okay? So that's sort of the ambient component, like, okay, in the presence of light, you put in like this sort of light-ish kind of thing around here, and it's going to color everything flat gray. And it's the product of the material ambient component and the light's ambient component. Or, sorry, that's the, what is CS? All right, I'm trying to figure out what this is. This is a general ambient component that doesn't apply to the light, and I think it's like the environment's component. Does somebody want to correct me here?
Yeah, it's an environment term.
I think it's an environmental thing. You say the environment has a certain color, even in the absence of light. Okay, you haven't even put in a light yet. It's sort of, yeah, maybe seen. That's good. I'm not sure. Okay, so M is material. I'm not sure what the C is. Okay, we'll forget it. Anyway, it's a scene-wide thing that doesn't have to do with the presence of any lights. Okay, then we have a bunch of lights, and for each light we're going to compute 3 components. One is the ambient component of the light. Okay, the light is shooting out blue light. It's going to color everything in the scene blue, whether anything can see the light or not. It's just going to kind of flood everything with blue, for instance. Okay? So we're going to have an ambient component of the material and an ambient component of the light. This is the diffuse component. Okay? What's the diffuse component of the light? It's you have something that isn't shiny, okay, like a piece of paper. All right? So assuming this is a piece of paper, it's going to get more light when it's looking straight at the light here than if it's here. Okay? So what we want to do is sort of compare the normal vector of the vertex with the normal vector of the light. And that's this dot product here. Okay? Dot product is great for comparing two normal vectors. All right? If you have normal vector and light vector pointing in the same direction, this component is 1. If you have the light component and the normal vector pointing in perpendicular directions, this component is 0. And it scales with this nice cosine characteristic there. All right? So you have a diffuse color there, and its strength is proportional to the dot product. Cool? Okay. Then the final one is what we call the specular component. This is sort of the shiny part. All right? So you look at my head. It's got some shiny components. I stand in front of a light. You're probably going to have like this shiny highlight right in front. I don't know. I can't really see. Nope, totally can't see. Although they will zoom in for me, which I really appreciate. Okay. If I put on like nice head grease every morning, then I can get a shiny component. A mirror is perfectly shiny. So some things you carry are shiny, some things are not. So this is also a dot product, but it's a dot product of what we call the half vector. So let me sort of, we have an eye. Okay, and we have a light here. Okay, and this goes in this direction, and this goes in this direction. The half vector is here. Okay, it's halfway between the eye vector and the light vector. And what this is saying is if the normal of the surface is in the same direction of the half vector, then we're going to have a shiny highlight. And this makes total sense if you think about a mirror, right? You have a mirror here. The shiny highlight is when the normal is halfway here because this angle equals this angle, right? So that's what the half vector is saying. So you dot the normal against the half vector, and note that it has an exponent there, this S exponent. So this is something else you set as far as the material. And so the S vector basically says if that characteristic looks nice, big, and wide like this, okay, like my head might be, or if it's a mirror, it's going to be really peaky, right? It's only specular for a very tiny set of angles. And so the higher the exponent, the more peaky that is. So you can play with the exponent that way. Okay. You can also calculate the light on both sides if you choose to.
So are these like ambient, diffuse, specular? These are just empirical terms that somebody came up with and said, this kind of models how physically photons would create light after they bounce off of an object?
Well, it's something you as the programmer specify. Okay, you as the programmer specify what these components are. And it's pretty much trial and error. So if you remember the GL tutorial, we had a picture of teapots. There was like 24 teapots. And they've just sort of said, okay, that kind of looks like emerald, right? So if we have these particular characteristics for the material, okay, and we say it's got this color ambient, and this color specular, and this color diffuse, that kind of looks like emerald. And this kind of looks like white plastic, and so on. It's just a guess.
I mean, it kind of feels like somebody just came up and said, yeah, it kind of looks like there's a specular components, we'll call that specular. And it kind of looks like there's some light that's not really shiny, so we'll call that diffuse. And
it's not very physically meaningful. It's like, does it have a shiny component? Because something like, like obsidian would have a very strong specular component, whereas if you built it out of rubber, it would not.
Okay. But I guess I'm just asking, like, is this just kind of made up and everybody went along with it, or have people kind of like done some studies that show, yeah, this is a pretty close approximation?
Well, it's not a close approximation. It's not a particularly good approximation. It's something that works. It's like, okay, artists need the ability to have an ambient component and a diffuse component because that lets us show this. And it'd be kind of nice to have a little shininess too, so we'll throw that in. It wasn't built to be physically realistic. This is not a very complicated equation, right? We're not doing any crazy math here. There's no physics, so it's simple, and that worked nice in 1982 when they thought up OpenGL. Today, you're going to write your own program that's going to do whatever you want. It's hopefully going to do something that's maybe more realistic.
Sure. Ray tracing do this also, or does it have a better way of?
So ray tracing could do this. So the process of how we're doing our rendering is different than the process of how we actually do our shading, right? So
okay, so this is completely different.
This is a lighting model that you could use in ray tracing if you wanted to.
Okay.
The right way to do it is something called a BRDF. It's a bidirectional reflectance distribution function. All right. So what I mean is, and you can actually calculate this empirically. You go out and you take an object, okay, like my fist here, and you put it in a dark room, and then you shine light on it from one direction, okay, and then you measure how the light bounces off of it in every direction, okay, and you do that for every direction. The incident light you vary over all directions, okay. So it's basically a four-dimensional function. Okay. The input is an angle, so you have sort of rho and theta, and the output is another rho and theta, so it's a four-dimensional function. It's actually even worse because you could make it a five-dimensional function if you include the wavelength of light that you're sending in, because red light might behave differently than green light. And it becomes a six-dimensional function if you put in time, because if you put in light and it's fluorescing, okay, then you're going to shoot in light and it might stay for a while and then like ramp off. So it's a very complicated function. So there's been a lot of recent work in computer graphics on how you actually use this and how you simplify that ginormous function which you can capture. That is something that's physically realistic. Okay? It's physically meaningful because you're capturing it physically. Actually doing the light calculations is pretty complicated.
Actually, OpenGL has a limitation of the number of the
lights.
Right. That's because of we have summation of the all the
okay.
all the
So
light.
OpenGL does have a limitation on the number of lights,
yes.
and the limitation is 8. Okay. OpenGL promises that an implementation will support 8 lights, but no more than 8 lights.
So is that has to do with the OpenGL stuff or just hardware? I mean,
okay. So what that has to do was, we've talked about having interfaces with state and interfaces that don't have state. Okay. OpenGL has state, but it's important when you have state to have a fixed amount of state. You can't have an unlimited amount of state, right? Hardware isn't very good at dealing with unlimited stuff. So they said, okay, we're going to pick a reasonable number of lights. That's how many we're going to support. We're going to have hardware support for any of these. If you want more, you can write a vertex program. Okay? But if we have 8 lights worth of state, then we know we're going to allocate space for those and no more. And then the programmers know we're going to have space for 8 and no more. Okay. Primitive assembly. Okay, so we got a bunch of vertices. We have to put them together into triangles. Okay, so not only do we have to send in a bunch of vertices, but we also have to send in connectivity information for these vertices. How do they mesh up with other vertices? Okay, how do they match up to make triangles? So that might be in the form of commands that say, okay, these are independent triangles or strips or meshes or anything else. Okay, so if you specify things that are not triangles, like you specify GL polygon, or you're doing quads. Okay? OpenGL suggests that you decompose those into triangles before you get to clipping, so that it'll be invariant if you do that. That it'll always work the same way. So primitive assembly is a little bit of a pain. It's good that it's always a fixed execution time. Okay? And that you can parallelize it very nicely. It's bad that this is sort of the first place where you have interdependencies between vertices. So that means there has to be communication between vertices to make this work, and that makes it a little tougher. Okay. Now, we'd like to reuse vertices as much as we can. Right? If we're doing my head and it's made of vertices, and we do independent triangles, then I'm going to end up doing, on average, every vertex 6 times. And calculating all the lighting to that vertex 6 times, that doesn't make sense. So we've already talked a little bit about how to make triangle strips, and that cuts down the vertex numbers by 3. So when you hear people say, my triangle rate is X, what that really means in your head is my vertex rate is X. Okay? Because on average, you're going to generate 1 triangle for every vertex. So even though I talk about triangle rate in class, it really means vertex rate. Okay. We'd like to do even better, though. It turns out we'd like to get more use than that. So Direct3D has indexed triangle strips. I think OpenGL is something like this right now. And so the way it works is that you send in one big mass of triangles. Okay, sorry, one big mass of vertices. and then you send in their connectivity information as a little tiny table. Okay, so you say, okay, triangle 1 is 0, 1, 2. Triangle 2 is 0, 2, 3. Triangle 3 is 2, 3, 5, and so on. Okay? So this is good because you have more flexibility than you do here. You can better do complicated strips and so on. And this takes very little space to take up. So you're going to get a win from being able to do that. More flexibility, but you have to send a little bit of connectivity information to make that work. Yes?
I have a question. In that case, we can apply one texture image to the whole the mesh. But if we want to sever multiple textures to the map into the the
Okay.
thing, so we have to each for example, vertex 1 has to two coordinate system, texture coordinate system. So.
So, okay, so let's say we wanted one texture, but we wanted to do one big mesh, but we wanted different textures here?
Yes.
Okay, so in general, you'd probably not want to do that. In general, what you'd probably want to do is say bind these textures, and then render all the geometry that uses those textures, and then you're done. And then you're not splitting it. Okay? If you were insisting that this part had to be a brick wall and this part had to be this nice wood pattern or something, then probably what you want to do is have two different texture coordinates at each vertex, and then you would have a fragment program select which one of those to texture from when it actually does the texturing. So it's possible to do that. The way that people pretty much, so what happens in practice a lot is that what you do is you say, okay, this is a brick wall, this is wood or something. What you do is you make one big texture that has both brick wall and wood in it. And so if you actually go look at like, Master Chief in Halo 2, like a guy, and he's got all these textures all over him, okay? And so you've got, 15 textures that make up Master Chief guy. Then what that actually happens in practice is there's one big texture that has all the textures from Master Chief guy in one texture, and it's called an atlas. Okay, so you put all these little textures into this atlas. And then you can specify one set of texture coordinates and you're done. Okay, because it's expensive to bind and rebind textures. And you can't do tricks like that. So, clipping. So there's actually two kinds of clipping that we have to worry about. And if you take a graphics class, they usually teach you how to clip line segments, which is easy, but not how to clip polygons, which is not easy. So if you have a point or a line, okay, then all you're really doing is eliminate geometry. If you're specifying points, it's either there or it's not. So all you can do is delete geometry. Okay, if you do a line, either it will delete the line or it will just change the line. Okay, so those are easy cases. Okay, they parallelize nicely. What is hard is polygons, because here we're going from having a triangle to having a quadrilateral. And we know we don't even render quadrilaterals. All we do is have triangles. So this is a big pain. Okay, clipping is hard. And clipping, especially in the early graphics hardware, this is really the thing that they tried to get right more than anything. This was really the tricky part, because this makes it really hard to parallelize. You go through all this stuff, you assemble into triangles, then you clip, and suddenly you got quadrilateral again, and now you have to go assemble it back into triangles and send them through and so on. So this is really a very hard thing. So we don't like that. It's hard for a couple of reasons. One is there's vertex interdependencies, okay, and that's not good. The second thing is that there's data-dependent execution, and we hate that. Right? Because, so let me ask, what's the worst case here? Right? If we have a triangle and a box, okay, and I was really mean and I specified the triangle in a bad way, okay, so I have some sort of triangle and I'm going to intersect it with this box, okay, how many-sided polygon could we end up with? Okay, so the picture here, we see that we could get a 4-sided polygon.
Had all points on the outside, and it kind of made like you could get 6 or 5 or 6.
You're saying I could have a 6-sided against a cube.
7, 8, 9, 10. Yep.
You just cut off the edges. I mean, cut off the corners.
You put each point like on the.
So let's make this an easier problem first. All right. Let's say I'm just doing it in 2D. What's the worst case?
2.
How bad can it be? Okay. So Okay, so now I've got 1, 2, 3, 4, 5, 6. Okay, so if you do it in, basically, I've put a line on the left, the right, the bottom, and the top. Okay, so if I added another dimension, then I would again have a cutoff at the front and the back. So I can actually make an 8-sided polygon if I have a really, really nasty triangle. Okay, and that's not good, because then you've got an 8-sided polygon you have to deal with. So then you have to decompose it back down to triangles and keep going. Okay, so to do this, I'm going to have to say, all right, I'm going to draw a line here, and here, and here, and here, and now I have 1, 2, 3, 4, 5 triangles where I first had 1. So you can see that this would be bad for parallelizing things. Okay, because you have this data-dependent step that goes in, and you don't know how much it's going to produce. It might produce 0, might produce 5. That's no good. So what we really try to do here is try to not clip. Okay, we're willing to do anything we can to not clip. And so this is kind of a cool algorithm. It's called guard band clipping. And so the goal here is we're willing to do extra work if it means we don't have to clip. So what we're going to do is usually we clip to the viewing frustum. We clip here, 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 and here. We're saying, gosh, if it would make our life easier, we're going to have a bigger viewport here. Okay, look, and now we don't have to clip this, and we don't have to clip this. We're going to have a bunch of extra stuff on the outside that we have to deal with, but maybe that's better than clipping. Okay, so let me sort of show you. All right, so here's our viewport, and then we put in this cool guard band. All right, so it means that for these two blue triangles, okay, I have to render the whole triangle. Okay, it means I'm going to do some work here that's useless and I'm going to throw away eventually, but I didn't have to clip that triangle. Okay? How about these red ones here? Well, we can look and see the red one is outside this line. This red one is outside this line. This red one is outside this line. Bam, we're done. Okay? We don't have to do these at all. Okay? We do have to clip this guy. If a polygon crosses the viewport line and the guard band line, then we know that we're going to have to clip it. Okay? But you notice when we look at this picture, we have to clip fewer triangles than we will if the size of the clipping band is the same as the size of the viewport. Okay? So we're going to have to do more work by having a guard band, but we're not going to have to clip as much. And we hate clipping. Clipping's really bad. Yeah.
So you size the guard band such that the clipping work, it's where the trade-off is between rendering and clipping?
Yes, that's probably fair. Okay? Rasterizing and clipping, or basically the whole rest of the pipeline and clipping. All right? The bigger the guard band, the more work you're going to do that you're going to have to throw away, but the less clipping you're going to have to do. So that's your trade-off. How much do you hate clipping? That's what we're trying to figure out. If you really hate clipping, you have a big guard band. If you don't mind clipping so much, then you have a small guard band. Now, there's some tricky cases here. Okay? This blue triangle is one that I'm going to render because I can't decide it's outside. Right? It's not all on this side of this line. It's not all on this side of this line. So I'm going to have to render this even though it's not going to be showing at all. Okay? This guy here I'm going to clip because it crosses both this line and this line, even though it's not there. Okay, even though we know it's not going to produce any pixels. So that's just an unfortunate consequence. But on the whole, we're going to get a win from this. Guard band is good. Okay, we really don't like clipping. Okay, next step is culling. Okay, and this is really pretty cool. Okay, so the question we're asking is a triangle facing toward the camera or away from the camera? Okay? And we can make this decision. Do we want to turn on culling or turn off culling? If we turn on culling, then it means that triangles that face away from the camera are ones that we're not going to draw. And usually that's really nice for like a watertight three-dimensional object. Because we want to render the front of that object, we don't want to render the back of that object. Okay? My head is a great example here. Now, we don't have a facet normal. Okay? Other APIs do, but we don't have a facet normal. Our normals are instead per vertex. So we can't really use a normal to figure this out. Okay? So instead what we're going to do is really very clever. Okay? we're going to use the sign of the primitives window area, and we're going to define the area of my triangle such that if it's facing the camera, it is a positive area. And if it is facing away from the camera, it is a negative area. And then we're only going to render the things with a positive area. You're going to say, well, that seems pretty cool because it's going to solve the problem, but what the heck do you mean by positive or negative area? Okay? So what we're going to do is we're going to, okay, so then we're going to say, is it positive or negative area? That'll tell us if we're on which side of the object, and we can throw it away if we're in culling. Okay? And one of the questions we asked earlier is, can we move that up? Yes, we could move this up. That's a possibility. Okay? So here's how we're going to define it. We're going to look at this triangle, and we're going to talk about its winding direction here. Okay? This one winds in this order. It goes 0, 1, 2. Right? It goes in sort of this counterclockwise order. It goes in the right-handed rule kind of order. Right? You stick this thumb out this way, and the triangle goes 0, 1, 2 there. Okay? If we switched 0 and 1, then it would be going the other way. It would be going 0, 1, 2. This is in a clockwise order. Okay? And we're going to define our area that way. Positive areas go in this winding order. Negative areas go in this winding order. And so if I specify all my triangles in counterclockwise order, let's say, okay, then when we look at the triangle, the ones that face toward the camera are going to appear counterclockwise. The ones that face away from the camera, we're going to be looking at their backside. Okay? So they're going to appear clockwise. So then we can take the area of the counterclockwise one and take the area of the clockwise one. This is going to be a positive area. This is going to be a negative area. And we can throw away the ones with the negative area.
But if we use triangle strip, one side is
Okay, so let's say we use a triangle strip because this is something the GL guys thought of. Okay, we want to use a triangle strip. 0, 1, 2, 3, 4, right? So we go 0, 1, 2, and that is in the way that I drew it, clockwise order. Okay, 1, 2, 3, also in clockwise order. 2, 3, 4, also in clockwise order. So all these are going to be the same. They thought about this. It turns out it works very nicely in if you do quads also. Like the order comes out right. Very smart. These guys totally nailed it.
Hey, I'm not seeing this. So 1, 2, 3, isn't that counter?
Oh wait. Okay. 0, 1, 2.
1, 2, and then 1, 2, 3 is counterclockwise, right?
Okay. This would be 1, 2, 3. Ah, crummy. Okay. So I promise they thought about this. They obviously thought about it more than I did. It might be, I'd have to look in the spec. My guess is the spec, I'm sure the spec does something about this, and it probably is that it specifies these, it always goes, it's going to get it right. So obviously I totally blew this, so I lied to you and said they're all in counterclockwise or clockwise order. I'm sure it gets it right, and they have them defined in such a way that it's always going to draw it the right way. Great question. It's the right question to ask. I don't have an answer for you right now.
So they consider the even number of the triangle.
You could say odd, even, odd, even. I'm sure they did something smarter than that. Okay? They thought about this is the right answer, even if I haven't.
They flip the sign of this computation as they go down the triangle strip.
So they go odd, even, odd, even? That doesn't seem fair.
Got to do something.
Do you really think that's what they do? Okay. I'll have to look because now I'm curious. So the OpenGL spec will be very straightforward about this way. What I'm guessing is they perturb the. I don't know what they do. I'll figure this out. Figure this out before next Tuesday.
So they don't use the normal at all then?
Correct, because we don't have a facet normal. We don't have a normal per triangle. We instead have normals per vertex. And what happens if two normals face this way and one normal faces this way? What do you do? Okay. Well, Wes suggests that's a bad triangle and we should throw it away. Okay. But do you have them both? So it's much. This is a very nice way to do it though, because this really does say which way it's facing. I mean, it's exactly right. If you have a closed solid, it is exactly doing the ones that you can see and you don't see. Like they totally nailed it. They picked the right way to do it. Okay. So this, yeah.
So if you have different normals for each vertex, that's not going to change whether or not it's facing toward you or away from you.
Correct.
It only affects the lighting.
Yes.
And so it
decouples the normal from the facing,
Right.
the windingness.
Right, and so during command processing, right, how do you solve the problem? Right, during command processing, you could add a stage that computed a normal as the cross product of a couple of edges of the triangle.
Well, I mean, practically, if you really wanted to do it that way, then you'd probably do it in the vertex program. Okay, but the problem is that there is no place in the command processor or the vertex processor that sees all three vertices together. You don't get all three vertices coming together until triangle assembly. So that doesn't happen in the command processor. The command processor doesn't get to see those three together. They haven't linked up yet. Okay, so what I've sort of said is we're going to have to decide based on the triangle and only on its position, not on its normal. We want to throw out the ones that face away from us. So the way we're going to do that is we're going to define the area in this crazy way so that positive things are what you want and negative things are not what you want. Okay? I'm saying that that relates to the windingness of the triangle, that if I switch these two, it's going to create a positive or a negative area as a result. What I haven't told you yet is how you actually compute area to do that. So it turns out, this is a very nice geometric utility here, that if we have these points on the triangle, we can calculate the area of the triangle using this equation. Okay? This is a very simple equation. Okay? This will tell us the area of the triangle, and not only will it tell us the area of the triangle, it's going to get the sign right. Okay? So all this stuff seemed like this is really confusing. Why do we have this negative area stuff? Negative area makes a lot of sense, and this is a really simple thing to be able to do. What's more, we're going to actually use this later on in the course. We'll use this in rasterization, so I want you to keep this in mind. What I'm saying is it's easy to calculate the area of the triangle. All we care about at this stage is the sign of this area. Is it a positive sign or is it a negative sign? Okay? What if it's 0?
It's a vertex.
It's not a vertex. It's still a triangle.
It's a point.
You were doing the right...
It's sideways.
Okay, it's sideways. Okay? Positive faces toward the camera. Negative faces away from the camera. 0 is head on. Right? So should you throw away 0?
Draw a line.
Okay, well, you probably throw it away because it doesn't have any area. Okay, a line is probably the wrong thing to do, actually. Okay, you do want to throw that away.
Isn't this still kind of expensive? I mean, you've got 5 plus, add, subtracts, and 1, 2, 3, 4, 5, 6, 7 multiply divides per triangle.
There's no divides.
Oh, well, divide by 2.
Well, but multiplied by 0.5.
Okay, so you still got 7 multiplies.
Okay, so there's a
triangle
cost associated to it, but compare that to like the lighting calculation. This is probably simpler than lighting. I mean, is it
Okay,
worth it
I
to do
guess
this because
that's
you're going to spend. I mean, okay, for a simple pipeline, roughly, okay, order of magnitude with no crazy vertex things, you're roughly going to spend about 100 ops per vertex and 100 ops per fragment.
Okay, so in the big scheme of things, this isn't that much.
Yeah, in the big scheme of things, you do 7 ops here, okay, or 12 ops here or something, and it saves you 1 fragment. That's a huge win. You definitely want to do that. Okay, so what is this operation mathematically? What are we actually doing here?
That's a cross product.
Okay, this is a cross product. Okay, so let me show what we're actually doing here. If you take this vector here, this is 0, 1, and 2, okay, and you take the cross product of that vector, remember the way you do that is you have this, how does this go? It's like the x direction, the y direction, the z direction. Then you have x0, y0, z0. I've done vector algebra in a long, long time. x2, y2, z2. And then you sort of do the multiply that way, subtract off that way. That's what we're actually doing here. What this calculates is this area. Okay, cross product calculates this area of this parallelogram. That's why we divide by 2, because it gives us the area of this triangle here, okay, which is nice. And keep in mind what it does is right-handed rule. What this cross product calculates is actually the length of this vector. The length of that vector is equal to the area of the parallelogram. And if you're in this winding direction, then it's this way. If it's in this winding direction, then it's that way. So this is positive area, this is negative area. So it's really nice math that works this all out. Well, this is not a lot of math to do, I think, in exchange for being able to throw out half your primitives. Okay? That's cool. Now, as a programmer, you get to pick whether or not you're, do you want to turn on culling or not. And you might not want to turn on culling. Okay, but you can pick when to do it. And if you've specified all your triangles right, so they're all clockwise or counterclockwise, you can pick that too. It's going to do the right thing.
Why divide by 2 then?
So you don't need to divide by 2 if all you want is the sign. Okay. Turns out later on we're going to want the area for something else, and we actually are going to divide by 2. Okay. So this tells us what the area is, but if all we're doing is culling, we don't have to do that. All we have to do is figure out if this is positive or negative. Okay. So I'm going to have to skip this, unfortunately. Okay, we'll go through this really fast. So this is sort of historical machines right here and how they organize their vertex units, which is kind of cool. Okay, so this was Jim Clark's geometry engine, so early SGI sort of stuff. Just to look at sort of how they organized it, what his genius was that he made a chip which he could replicate 12 times, and it would do all the steps of the geometry pipeline. 4 of those chips would do the coordinate transformation. Half of his entire geometry pipeline did nothing but clipping. Okay? It clipped against left, right, back, front, up, down. Okay? So each one of these does one clipping plane. And then he had one doing the divider and one doing the viewport.
Well, what was each step of the transfer? Well, for like one for projection, one for... No.
It was a 4x4 dot product, right?
Right. Oh, okay.
So each one of those did one line of the dot product. Okay? There wasn't any lighting in this. Okay? So clipping at half the power of the machine, it was performance invariant. It didn't matter if it was clipped or not. But usually those things sat idle, and that was not so good. Okay? Let's see. So then they added lighting in the next one. So they had fill hardware and so on. Okay? So they had 5 engines that were identical. Okay, so this had clipping that was a fifth the power. Kurt actually gave this lecture at one point. So what they had, what SGI talked about and other companies talk about now is they talk about the fast path through the hardware. So there's certain modes you can set up that are going to run through the hardware fast. Okay, they're going to take maximum speed of the hardware. So not everything is in the fast path. Some things are fast, and some things are going to have to drop back to software or go through other paths, and they're going to be slow. So what Kurt said was that originally, based on what they had, they tried to do lighting, and they tried to do the whole lighting model in one pass. Like they tried to put all of lighting in one pass, and they couldn't make specular fit. And he said that Dan Baum earned a case of beer for being able to fit specular lighting in the fast path when they actually implemented this thing. So the reason that specular lighting was possible and fast is because Dan Baum really wanted a case of beer. Okay, so here clipping didn't have quite so much of the power. If you actually did clip, then it ended up slowing the pipeline execution, which was not so good. We'll talk about this later on when we talk about parallelism in general. Now look how we're moving from having this linear chain of processors, and as the processors get more powerful, then each one can do more and more, and as you want more parallelism, they get wide, right? So here everybody's doing like 1/5 of the work. Okay. The next generation, we had 8 things, each of one of which could do the whole work. Okay. So this is how SGI started growing, right? They had more and more powerful processors, and this could have a much better throughput. So the real task here is the command processor, which sort of had to deal out work to each of the engines here. Let's see. The way that it worked is it would take this big long strip of primitives, and it would send an entire strip of primitives to a different engine. So it would take a bunch, send it here, a bunch, send it here, a bunch, send it here, and so on. I believe this one was round robin. Yeah. So that was fairly good, but it turned out the next one was better. This had some round robin. Okay. Sorry, this is just how we did clipping. The next one was the infinite reality, and so this was better than round robin. It would do least busy work assignment. So it would always send it to the geometry processor that had the least amount to do. So these started having, all right, okay. So I can't go through this in a lot of time. Okay, this was also the one that implemented the guard band. So first time they had guard band was in this particular bit of hardware. what geometry engines evidently did in 2001 was they had a rasterizer in 2001 that didn't do any clipping at all. Okay, because clipping was such a pain in the butt, they had a rasterizer that would do all the clipping in the rasterizer. And so that had more work because you would go through the entire geometry pipeline for everything, whether it was clipped or not. You never threw away anything. The clipping was such a pain, you were willing to pay that extra price and let the rasterizer take care of it. So they had a rasterization algorithm at that point that did it. I've heard they've gone back to doing standard clipping with rasterization now. But, I mean, it's a constantly changing thing. Okay. Let's see. A few minor topics sort of here at the end, so I'm going to go through them for the next 3 minutes until we're done. The first one is an issue of having display lists. So everything we've been talking about so far has been this immediate mode kind of rendering, where you're sending things through just one at a time, and it's able to handle them one at a time. It renders them immediately when they get them. What if we want to basically have a procedure call? Okay, that's, I want to render this bit of geometry. That's what a display list kind of is. It's a retain mode construct. You specify it first, and then you can call it just like a procedure call. So it's very useful when you have something you're going to reuse a lot. So you're going to have one piece of reusable static geometry that you're going to use over and over. Well, what the display list can do is you bundle up that geometry, you compile it, you send it over to the GPU, and you don't ever have to send it again. You can just call it again and again, and you don't have to keep sending the vertices over and over when you call it more than once. This is good because what we're trying to do is reduce that bandwidth. So if we can leave some of those vertices we're going to reuse over on the GPU, that is obviously a win for us. So there's lots of things people usually put in display lists so they don't have to specify them over again. Okay. All right, so this is the last thing that I'm going to cover. And we'll pick this back up. But this is a very important point. So the move is away from immediate mode things. And the reason is because what we want to actually send is chunks of things. It's more efficient for us to send chunks of things. Anything has a cost for 0 bytes and then a cost per byte that we need to send. So what we want to do is send this giant chunk of data over at the same time. That would be good for us. So the way that people generally do this now is they take a whole bunch of vertices and they put them all together into a buffer or an array, and they send the whole array over, and it's got a big list of triangles to draw. Okay, and you only have to make one call to send that over, instead of having to say, send a vertex, send a vertex, send a vertex, which is what happens when you call GL translate all the time, or GL vertex all the time. So this is what Graphics Bench does, if you've been looking at it. It uses these sort of vertex things. Everybody does this, and I'm going to show you why. Okay? So every time we send one of these, okay, every time we say, basically, draw, we're going to call that a batch. Okay? This is a batch of elements that we are rendering. And so this is, it's a few years old right now. NVIDIA presented this at the Game Developers Conference, but they're showing batch size performance as a function of the number of triangles per batch. Okay? If you don't have very many triangles in every batch, then you are completely limited by the number of batches that you have. In this whole range right here, the more stuff you put per batch, the better performance you get. Okay? This is performance. Okay? What that says is it doesn't matter how many triangles you put in per batch. You're completely limited by the number of batches that you can actually launch. Okay? Your bottleneck is not your GPU. Your bottleneck is your CPU saying, I'd like to kick off another batch. Okay? That's the big picture here, and this is why we batch things. Eventually, we get over to the point with big batches that are limited by the kind of GPU you have. Okay? That's the case over here. But if you don't have a lot of work per batch, you are completely limited by your CPU. And so the nice part about the Game Developers Conference is they treat you like you're stupid, and they put like multiple slides in that are very, very simple. So they're saying if you don't have a lot of triangles per batch, you are limited by your CPU because all it does is submit batches. Okay? Your GPU is just sitting around twiddling its thumb. Okay? So they they just dumb it down more and more and more, right? That's what you get. Okay? And then they get, please hang over your bed. So they're basically saying whatever you do, you're going to get 25,000 batches per second. You get to pick how big that batch is. Okay? But it's very important to batch things up. This is why, generally for performance, you don't do immediate mode anymore. It's why Graphics Bench doesn't do immediate mode. It's why it puts it into a vertex array. Or else it's going to be limited by the CPU. So you get to do as many triangles per batch as you want. Okay? There's a few reasons why you might not want to have a lot, but pretty much you don't want to be CPU bound. Okay? You want to have a lot of work per batch. We're done, and we'll take this up in a second because I'm already past time.
Okay. I was just going to ask, why is this not done in a compiler? Like, why isn't it done, like, you can do an immediate mode and then the compiler will change it to this mode?
In theory, I think you could. That's a really good question to ask the compiler people. I think that's a really good question. It might be that it's just very complicated to do that. In practice, the GPU does batch up commands, okay, and usually it's called a push buffer, and it builds this whole push buffer, and then it pushes it once it gets big enough. But what it's generally bundling up is the commands that you specify. And if you specify GL vertex, GL vertex, GL vertex, I'm not sure that it's smart enough to figure out, okay, we can actually put those all in an array.
Okay.
Good question, though.
Yeah.
So under what conditions might it be the case that pure retain mode, build something up with display list, would perform less poorly than what looks like immediate mode dispatching, out these calls, out these batches?
You would like to think that it probably never will. I mean, retain mode is probably not a disadvantage, except that it's harder for you to deal with as a programmer. Immediate mode is very simple for you to deal with as a programmer.
So I have observed conditions
Okay.
in which this happens, and it's always been very perplexing.
So there's people who are better programmers than me who might be able to answer that. I would think that if the drivers do a bad job of managing display lists and figuring out what to leave on the GPU, or if you're spending all this effort, optimizing a display list that you call once, because there's extra effort associated with it, that could be a problem.
It gets even worse.
Okay.
If you put a vertex array inside a display list, it performs more poorly than just calling the vertex array over and over again.
So this is a difficult and very specific question, but that's the sort of issue you do want to raise with the vendors, because I don't think theoretically there's a reason you should be seeing that, but there's a lot of practical reasons why perhaps you may. Awesome. Have a good weekend, guys.
So my CPU is actually my bottleneck, I think, for a lot of my tests.